Now I want to give a summary to several types of knapsack DP problems. So first, there's a link to the useful guide on knapsack DP, which link to a number of problems, knapsack DP, and also provide a solution code for one of them. So I want to first let's look at the one version of this 0-1 knapsack problem. So the point I'm trying to get across is depending on the parameters, the same problem will be solved in different ways. So we have this is knapsack problem. We have n items. We have each one has a weight and a value. We want to select some item to put in a knapsack with a capacity, maximum total weight, and we want to get the maximum total value. So here we have, let's say we have up to 100 items, and the value of each one is up to 10 to the 9. The value of the total weight is up to 10 to the 5, and the value of the weight of each item is less than this. So how do we solve this? So let's define the DP state. So one way to solve it is that we can define dpij to be the maximum value that can be obtained under weight j using the first I items. And these will have the j index will go up to w, and the I index will go up to n. So the complexity is or nw. So for this problem, it is fine, because the computation for each cell is a relatively simple computation. So the constant factor is not large, and this can be solved using just 1D array for W. So using similar technique to technique similar to what we talked about in the last problem, this 0-1s. So this is fine. Now let's look at the same problem with parameter difference. So this time the weight can be large. The maximum weight, instead of 10 to the 5, let's say it's up to 10 to the 9. Now we cannot use the same problem as before. But this problem have the feature that the value range is small. So then we can solve this by slightly changing the DP state. So we define DP over all possible value. So if we use a 2D array, it'll be what is the minimum weight we can reach using the first I items, and the minimum weight we need to reach, and the reaching a value of this particular value. So then the second dimension in the array will be over value instead of over weight, and we do that because the maximum possible value here would be 10 to the power of 5. So it's a smaller. So again, this can also be solved using actually that's yeah, I think using, I'm not totally sure this it should be doable. Okay, now let's look at another version. This time both W and V are large, so we cannot use the method that we used before. So in general, this is actually, if there's no other special structure, then the problem will be NP complete. Well, the problem, there's no other restriction on these values, but it can be solved in exponential time. And this problem have n up to 20, so then that means we can tolerate the 2 to the n complexity algorithm, or this I think n times 2 to the n. So we just consider all subsets. So enumerate through all subsets, and then we can find out whether one of them will be able to do that. I think this problem we should also be able to go up to n up to 40. By that time we will be using meet in the middle. So we divide the n items into two subsets, each of them half n, so up to 20. We compute their all subset and we store that, and then we can scan through the two sub-solution to get the answer. So that's 0-1 knapsack problem. Now let's consider a harder variant. So we have so this question is defined using numbers instead of items. So we have a number of I guess types of item is small, up to 100, but each of them may appear many times. So each of them may appear up to 10 to the 5 times. So here we just use that as number. So we have up to n numbers, and each of these number can be fairly large, and then each of them can appear a fairly large number of times. And we need to determine whether we can choose some number among them so that they sum up to k, and k is up to 10 to the 5. So yeah, so this problem it have similarity to the 0-1 knapsack, also to the coin exchange and equal subset sum problems, which were covered in the video by Chung. So how do we if we solve it using a similar method, what will be the time complexity? So I would like you to think that through and see whether that will be efficient enough. So here is what I see if I apply the standard approach. So we have, if we define dpij to be whether we can use the first I items to sum up to j, then the dpij would be true if and only if there exists x. So x is the number of the ith item, s number we're going to use. So x can be as small as 0 and as large as mi, the number of ai's. And then we dp I minus 1, j minus x times ai is true. So if we can find such x, then dpij should be true. If we cannot, then dpij should be false. So, but the naive implementation of this will have a complexity of n times k times m, because to fill this one cell, it appears we'll be looping through this x. So, but the computation of doing this is actually, we are actually repeating a lot of the checks. So, for example, suppose we try to fill dpij. Then we will be first looking at the dp I minus 1j, which corresponds with x to be 0. If that is true, then this should also be true. Then we will be looking at the dp I minus 1 j minus ai, so we use the one of them. And if that is true, then this should be true. However, we are repeating this check when we are trying to fill dpi j minus ai. So because there we'll be also checking dpi minus 1 j minus ai. So it's just that when we are considering j minus ai, when we check this, it's we're trying to see whether we can use a 0 of this to form j minus ai. So in other words, if we can fill so then this check can be done by checking dp I j minus ai. However, if we just use a Boolean array of true false, that will not be enough, because we need to know how many AIs we have used to reach j minus ai. If we use too many, then this is not feasible. So then that means that we need to, the state we need is not enough. Just having true false is not. We also need to know when we are reaching this, how many of the ice item have we used. If we keep track of that information, then this computation can be efficient. So this is a way of using that idea. So we define dpij to be the maximum number of AI that are left when we're using the first I numbers to make j. And this is a -1 if it is impossible. So then we compute dpij. We'll do there will be 3 cases. First is we look at dpi-1j. So basically we're trying to see can we do it without using any of AI. If that is greater than or equal to 0, then that means we can make a value j without using any of AI. So then we simply set dpij to be mi. If that is less than 0, then we need to check, can we do it by using one more AI. So then we, instead of looking at dpi-1, we will look at dpi-j minus AI. So we'll be looking at, can I reach the state using the first I items to reach j minus AI? And if we can do that, while still have AI left, then that will then we can reach this. It's just that we'll be using one more AI. So that will be this part. So this part is a part that is possible. So if dp i-1j is greater than 0, then we will use this. The other part is we cannot reach this state. So this will happen either when we cannot reach j minus AI, or we can reach j minus AI, but by that point we have used up all the AIs. So then we cannot reach this dpij, reach the value j. By changing the array from Boolean array true false to store this extra state information, we reduced the complexity. So we have enough state information so that we don't have to repeat the computation. So this, if this is your first time examining a problem like this may look confusing. So I encourage you to look at the slides a couple of times, and maybe also watch the video a couple of times, and hopefully the video help a little bit in understanding this. So I think that's all I want to say on knapsack problems.